Alright, for this video I want to go through how to write a prelab entry in your notebook. This is new for everyone, even if you had me for Organic Chemistry 1, because we didn't do many reactions in Organic Chemistry 1. In Organic Chemistry 2, we are running mostly reactions where we are going to be interested in the stoichiometry, um, the amount made, the theoretical amount expected, percent yield, and that will require a different type of prelab entry than what we are used to. Now, everything in pink are just notes. I wouldn't expect to see this on your prelab entry when you hand in pages from your notebook. But definitely, you need a page number, and whoops, I'm on page 41 in my notebook right now, a date, and the title. And the title for lab number 1 is sodium borohydride reduction, or you could just write BH4 reduction of cyclohexanone. As a reminder, your lab notebook should have no pen, no erasing, or whiteout or blackout. There's another one. Oh, yeah, only write on the right-hand side of your notebook. My notebook, the ink bleeds through, so when I take pictures of my pages, if there's any writing on the back, it tends to be a little bit hard to read. Okay. After the title, well, we have a reaction, and the purpose of what I want to put after the title is the reason why I want to do this is I want to be able to glance at your notebook and instantaneously know what the reaction was about, what the lab was about, and what was the key, feature or the key thing that we were learning. A good place to start is, though, the reaction. Okay, this is a good pictorial that tells me what reaction we are doing at the top of your first page of the lab. MEOH, H2O, HCl. And from the handout, I do use some number notations. When we write the procedure, I don't want to keep saying cyclohexanone over and over again. I could just use 1 with a tilde underneath. Now, if we were typing this or if we were doing electronic drawings, that 1 would be in bold. I'm going to call this product. Okay. And the product is what? We'll give it the name cyclohexanol. Okay, that is our product. Later on, and what's going to be required every time we do a reaction is I want the theoretical yield nearby your picture of the product. So I'm going to put a little box here as a reminder. That's going to be in what? In grams. Okay, we'll do those calculations later. Reading through the procedure, it seems like you're going to run the reaction and you're going to hydrolyze it with iced acid. So there's the ice. And you're going to do a purification with extraction. And then at the very bottom, we're going to calculate the percent yield. Okay. I do want to sort of give the reader a clue as to how we're going to work up the reaction. Work up meaning how we're going to purify the reaction. And so maybe I'll just put a little picture of a separatory funnel. There isn't much in terms of specialized glassware we're using in this lab. Um, let's see, but maybe can I put the different phases? It seems like it's going to be mostly water, right? Because here we have water. That's going to be one of the layers. And the hmm, oh, diethyl ether. And diethyl ether is less dense. Uh, so maybe we could say here Et2O, and then this is the aqueous. We could put water. Actually, your methanol is very water soluble. So when you do the extraction, probably, well, we're hoping all of the methanol goes into the water layer. Your product should go into the ether layer. And we could put here product, hopefully. Okay. That's a good enough picture for me. If we were running a reflux, then probably I would expect you to draw the condenser tube. Um, if we were doing a distillation, I would ask for the drawing of that glassware. But I think this is good. Nothing too special about. Ooh, the one kind of weird thing about this reaction is that the ratio is not 1 to 1 to 1, right? We don't have one starting material, one reagent, one product. It is actually, and I would put this on the cartoon portion, we have one, it's called equivalent, okay, to every 4 equivalents. Now that is theoretical, okay, that is just based on the mechanism. It's not based on the actual amounts that we are going to use in the experiment. Many times, or equivalents, many times the scientists will kind of err to one of the reagents, maybe make one a little bit more excess than the other. Uh, just there are certain reasons why you would make one reagent more than the other in terms of excess. It probably has to do a lot with purification. Is it easier to purify excess sodium borohydride, or is it easier to purify excess cyclohexanone? Or you may want to give excess reagent to make sure that all of your organic starting material turns into the product. Okay, so those are some strategies by which people design syntheses to figure out, well, do I really want to have excess? And if I do, which component do I want to be in excess? Next is, I think last semester we had the purpose. Okay. The purpose is just a direct statement of what you are doing in this lab, plus maybe some flavor. Like if we're doing a reflux, I would mention that we're doing a reflux. Or if something is unusual about the type of extraction, I would mention that in the purpose. We are using a reagent that's we haven't used before, sodium borohydride. So the purpose, I would say, is to synthesize. Okay, that's literally what we are trying to do. Cyclohexanol via NABH4 reduction of cyclohexanone. Now, is there anything else I want to say, sort of to give it also, like, kind of highlight what is so special about this experiment? Mm, honestly, um, I might want to say something about the stoichiometry. I might want to say how we actually isolate this because there is a new technique called rotary evaporator, which we're not going to go over in this lab, but probably I'll show a video later on in the summer. So if we're not going to talk about that, I'm just going to skip that. But we do. Let me figure out a way to figure out. Let me figure out a way to incorporate this stoichiometry to synthesize cyclohexanol via NABH4 reduction of cyclohexanone. Um, mm, mm, mm. Okay, how about this? Maybe colon or semicolon, a reaction that has a starting material, reagent, product ratio of 4:1:4. I like that. Definitely, we have not seen a reaction in organic 1 where we have such a ratio that deviates from 1:1:1. This is what makes this reaction special. This is what makes it worthy, in my opinion, to do this reaction in lab to get you experience working with reactions that are not 1:1:1 ratios. Okay. All right, I'm good with that. Source. By the way, you want to use this as a template for the rest of your prelab entries because there are prelab entries or there are purposes that aren't really purposes, right? I mentioned this last semester. For instance, appreciating organic chemistry and all of its wonders and subtleties. That's not a purpose. That's a byproduct or that's an aspiration, but that's not a purpose. Heck, even saying to, I don't know, to learn how to make alcohols from ketones. That's not really the purpose. That is a general theme, but that's not the purpose. Okay. This is, for me, a sufficient purpose, and you want to follow something like this for every single lab experiment that you write about. The source is going to be lab handout 1 or lab 1 handout, okay, and several videos. Well, the pre-lab lecture is always going to be a constant, so I wouldn't say that. That's it. Just a lab 1 handout. Okay. Next is something that's different, and it's the stoichiometry table. Okay. We are going to have a column for the compound, and we'll abbreviate this CMPD. And you're not going to list everything. For the stoichiometry table, you are going to list the materials that reflect or affect the theoretical yield and the percent yield. Okay. Definitely the cyclohexanone. And see, that's why I use notation so I don't have to write cyclohexanone every single time. Definitely your NABH4. What I am leaving out is the methanol. When you read the procedure, you should be able to guess that methanol is just a solvent. HCl in water is sort of like the workup when we try to hydrolyze the borate ester. We have excess of this, okay? And maybe during lab I would have told you that, or before lab I would have told you that. So reagents that are in much, much, much excess or solvent, you just don't worry about, okay? It doesn't affect, right, your decision on what a delimiting reagent is. The last compound I do want to put is the product, and we could abbreviate it PROD. Okay. Next thing is the amount. Yeah, the amount. And normally you want it in grams, but for the first compound, it is in milliliters, and it's 5.0 milliliters. Right. Hopefully, on a scratch sheet of paper or um, or in your notebook, you had already figured out the amount in grams. Okay. So what I'm thinking about is that the calculation for the limiting reagent that we did in the previous video. Because that's what I want. I want the amount actually in grams, and the density is 0.95. So 5 times 0.95 grams per milliliter. Okay, I got 4.75 grams. Okay, that's an amount. I wanted this in grams because later on, or the next column, we're going to figure out millimoles. Okay, not moles, but millimoles, and we'll see that in just a bit. The sodium borohydride is 1.0 grams. Okay. How do you figure out the millimoles? Well, we need the molar mass. And again, when you did the calculation to determine the limiting reactant, we looked up the molar mass or the molecular weight of each of these components. Okay. The molecular weight for one is 98.5. So 4.75 divided by 98.5. Okay, that's what I got for moles. I don't normally like to write a lot of zeros, so we're going to convert it to millimoles. So we're going to multiply by 1,000. 48.2 millimoles. Okay. We'll put the units. Let's do sodium borohydride. 1 divided by, and the molar mass for that is 37.83 times 1,000. Right? There's 1,000 millimoles in a mole. 26.4. Okay. Oh, millimole. Now, if you're just looking at the millimoles, you might be fooled, right, into thinking that the limiting reactant is sodium borohydride. But, in the previous video, we showed that sodium borohydride is actually in excess because 1 mole of this can actually react with 4 moles of your starting material. So technically, I could actually have close to or over 100 millimoles of 1 and still be able to convert all of that, reduce all of that into the cyclohexanol. This amount of sodium borohydride can take care of over 100 millimoles because I'm multiplying this by 4. I'm not showing you those calculations because we did those in the previous video. I am looking at my calculations from that previous video, okay, where we figured out limiting reactant. Remember how this was the limiting reactant? Okay. Let's not worry about that just yet. Now you have to do equivalence. This is where people get confused, but you don't have to be confused. It's not that difficult. Equivalence don't look at the 4:1 to 1, the 4:1 to 4 ratio. Forget about that. Equivalence is just based on the millimole. Equivalence is just based on the millimole. Now the thing that is important is that you set the limiting reactant as 1 equivalent. Okay. What was our limiting reactant? Our limiting reactant was cyclohexanone. Okay. This was all calculations done before, right? So you would want to do those calculations first before you start your pre-lab entry. Okay, so cyclohexanone is my limiting reactant, and I am setting it purposefully as 1. So this is the LR. See, we're not getting this from the millimoles, right? We're getting this from our calculations. Now, what you want to think about is, what is X? What is X? Okay, in pink, let me show you. You don't write this, but try to understand what I'm doing. 48.2 is to 1 as what? 26.4 is to X. That X goes now here. Okay? What number do you expect? You expect this number to be lower, to be smaller than 1, because this number is smaller than 48.2. I'm not sure where the disconnect is. This is on a video, so you could always refer back to it, but every semester, 10% of the class still doesn't get equivalence by the end of the last lab. You got to understand this. Just do this calculation. Literally, you could put an equal sign here. Solve for X. 26.4 times 1, so I'm cross-multiplying, divided by 48.2, 0.55. Okay. Again, this 1 indicates to me that you know that this is a limiting reactant, but in terms of overall amount, we have a 0.5 to 1 ratio. Okay. Again, I'm not looking at the 4 to 1 to 4 ratio. I I did do that to figure out the limiting reactant, but for the equivalence, you ignore that. This is just straight up what is the ratio between these two, regardless of how much is needed to make a product. Okay. If this is the limiting reactant, and it is, and again, I'm not redoing the calculations, we've done those before. There it is. Okay. How many millimoles do you expect of the product? You would expect 48.2 millimoles of product, right? This is the analogy of sandwiches, right? How many sandwiches would you expect if you have this many pieces of cheese? Okay. Now, I'm going to put here expected. Remember, this line is for the product. Okay. Then what is the amount? I should have looked this up. Oh, I did. I do have this number. I need to multiply the moles times the molar mass, the molecular weight, which is 100.16 grams per mole. But how many moles do I have? I have 48.2 millimoles, so I'm going to multiply by 0.048, right? That's how many moles I have. 2. Hopefully this number looks good. Okay, that looks reasonable. 4.83 grams. 4.83 grams, and that is expected again. Expected. So, this last column or this last row, it's not actual measurements, it's calculations. Now these are measurements. We are literally measuring 5.0 milliliters, 1.0 grams, and doing the reaction. Okay. Don't worry about the equivalence for the product. That doesn't really matter or doesn't make sense to put it there. But these numbers are super important. The 48.3 grams, which came from the 48.2. It only looks very similar because the molar mass is approximately 100 grams. So that is the number. Do you remember what we need to do with this? Up here. 4.83. Okay? Think about what I am looking for lab 2. In lab 2, you are going to run a reaction and look at what I am expecting for lab 2 in terms of your cartoon. Okay? Look at what is expected for the purpose. Look at what is expected for your stoichiometry table. Okay? This is going to take rewatching this. I would rewatch this video one more time before you do lab 2. Okay, but right now, this is the pre-lab entry so far that I would expect for lab 1. Okay, give or take some other details that you may want to add, but this is pretty good. The last thing we just do in your pre-lab entry is a procedure that I'm not going to do with you. You're going to do that on your own. A procedure. Now the procedure you are following obviously the handout, and I want this to be either numbered steps or bulleted steps. Okay, doesn't matter which one you use. All right. When you're done with the procedure, that is what I expect if we were meeting face to face for you to show me before you touch any glassware. Okay. All right. I think that's good. Good. I like that. I'm going to post on Moodle the instructions for the lab notebook and also the post-lab questions. They're going to be pretty straightforward. Right now, lab 1 is just to get your feet wet in terms of what I am expecting from now on for your pre-lab, for your pre-lab entry.